And I will pass it over to Dave, who is going to take us through some of the work he's been doing, along with Roger, who you guys met earlier, and a number of other players at R3 in Singapore.
Hi. Is my mic working? Yeah, okay. So I get the benefit of actually being able to do something a little bit different to what everybody else has been doing today. So everybody else has been talking about all the really cool stuff that we're doing inside of Corda as a platform. And I get to talk about using Corda as a platform. So a bit of background for me, I came in about 3 months ago and looking at how we use Corda as a platform to solve interesting customer applications. So I'm part of the solution architecture team. There are a bunch of us around. In fact, there's a few in the audience here, so you can catch up with some of us later on as well. So I'm going to talk a little bit about cache in the world of distributed ledgers. I'm not actually going to talk so much about the cache part. I'm more than happy to talk with anybody about that later. I'll give a very, very quick overview of what we're doing as we're going along, because what I really wanted to do is talk about something interesting about Corda and how we can do something with Corda that we think is actually pretty cool and we think is actually very difficult to do in most other platforms that we've encountered. So what makes cache interesting? So we figure there's some really interesting things about cache, and why are we interested for building stuff on Corda? So it's a building block for most financial applications. It goes without saying. It's fungible. We can exchange one piece of cache with another piece of cache, and it's just the same. It works just fine. We can exchange it for other assets. We can describe rewards and penalties. There's all sorts of things here. Cache is like this foundational building block. We can use it to make promises, and one of the interesting things we want to be able to do is we want to be able to settle it now or in the future. So if people are familiar with cryptocurrencies, they're used to the idea of settling it now, as long as you've got some sort of probabilistic finality. But we'd like to be able to settle it in the future, or we'd like to be able to say, we'd like to promise to do something and do it sometime later, but we might not necessarily have the funds available to do it right this moment. So this brings us on to what I really want to talk about, which is deferred net settlement. For anybody who's familiar with RTGS systems, real-time gross settlement systems, this is sometimes known as a liquidity savings mechanism. So a very quick tutorial, because I'm not sure how many people are familiar with this. I suspect a reasonable number aren't, so I will try and make this fairly quick. So we have a simple example here. We have two people. We have Alice and Bob. They both owe each other some money, so they promise that they're going to pay some money at some point in the future. And they both have a certain amount of money available to them right now. So in this particular case, Alice owes Bob $7. Bob owes Alice $8. They could actually both pay, because they actually do have $10 each. But for whatever reason, they decide they don't want to pay it yet. Maybe they both owe somebody else $5, and that's more important. So that they're going to come along and say, well, we're not prepared to settle this just yet. But if you look at this as a problem, they both owe each other money. And so the amount of money they really need to exchange is far less. So these are actually promises to pay, not actual payments. I just need to make that clear. So they owe each other money. And so we can't create a transaction that will mutually move this money around because of the way that Corda actually handles states. So we can't actually move money from Alice to Bob and Bob to Alice if they don't actually have the money that they're going to be dealing with. And in the case if the starting balance was too low, they wouldn't actually have the money to start with. So that's just something to bear in mind. So in this particular case, we can resolve things very, very simply, because in fact the net payment here is that Bob can pay Alice $1 and actually settle out both of those obligations. And the reason this is interesting is we started out with two obligations. We're representing two different things, two different financial contracts, and we're going to settle them with a single payment. So we're going to actually settle it with one. In fact, if they owed each other the same amount of money, you could actually settle both of their obligations with no money at all. So this is actually a class of interesting problem where you really want to be able to do 2 or 3 things at the same time. You want to settle the obligations that they have to each other, and you want to make a cash payment at the same time, and you really want to make these things happen at exactly the same time. So you really want atomicity here, because otherwise you have a potential problem where part of the system is unwound and part of it is cancelled out, but maybe the payment doesn't go through properly, or maybe the payment goes through but some of the obligations aren't settled correctly. So there's a real need to try and make these things appear to happen simultaneously. So that was a simple case. A slightly more tricky case, and I'll try not to belabor them, but slightly more tricky case, we've got 3 people who owe each other money. This time we have Charles as well. For anybody who's observant, you'll actually notice the amounts they owe each other are more than they all have. so that no one of them can actually make a payment here at all. But because there's a cycle of money, and the money goes round in a cycle, then you can actually settle this on a net basis. So in fact, for anybody who doesn't want to do the maths, here's actually what the resolution looks like. And in this particular case, Charles ends up owing both parties money. But the interesting thing here is that Charles ends up owing Bob money, but actually it was Bob that owed Charles money in the first place. That was actually the obligation. So the net settlement actually reverses the direction in terms of actually solving this. So I've mentioned, in fact, that both payments have to occur simultaneously. This is actually really important. When we settle this out, if that $4 was paid, but the $2 wasn't paid, then in fact we've now ended up making a payment that makes no sense at all, because it doesn't settle anything that anybody cared about. It just leaves the whole system in complete state of chaos. So this atomicity thing is really, really important. So final example of in the tutorial bit here, we've got 4 parties. We've actually added another one in here, Demi. And the interesting thing here is to bear in mind that Bob and Charles don't have any payments between each other, and Alice and Demi don't have any payments. But if you were to actually look at the netting calculation and look at how this resolves out, what you actually find is that the netting solution involves Demi paying Alice. And as I noted before, all 3 payments now have to happen simultaneously. We now have 3 payments that must happen at the same time to settle 4 payment obligations. So there's now 7 pieces to this that all have to happen at the same time. The interesting thing here is that, pardon me, Demi now ends up owing Alice money as part of this net settlement, but they didn't actually have a relationship. In this particular case, Demi may not even know who Alice is, but in order to settle this out on a net basis, there has to be this payment that's made. So that sort of gives a flavor of the sort of problem that we're dealing with. And that last one's actually interesting, and it sort of links in with the stuff that Kostas and Mike were talking about. It links in with some aspects of privacy and how we think about protecting information inside of a distributed ledger platform, because in this particular case, we're having to make payments between people who don't necessarily know each other, or don't need, or we wouldn't want them to know about the fact that there were other payment relationships involved in this net settlement. So the real world is a little bit more complex. So that was the simple tutorial example. So here is a more complex example, and this is involves an awful lot more people. I had to shorten them all to letters because it wouldn't fit. And you notice that some of these actually owe each other money. Some of them have quite complex payment cycles. Some of them are just normal payments. And so what we're actually modeling here is something that we might actually find between say, a network of banks. I mentioned that these are a network of banks because that's actually the problem that we were solving. But actually, the same ideas and the same concepts are applicable in any number of scenarios where there's some sort of fungible asset that can actually be transacted between multiple parties. So in this particular scenario, you can imagine lots and lots of different ways that you might actually provide some sort of netting. A really simple one, if anybody's looking at the top, and you see between nodes D and F, they owe each other money. Potentially, they could net something between themselves. There are lots of other cycles in the system, so between nodes F, E, D, and F, there's a cycle again. And actually, if you look at this whole thing, there are actually several dozen payment cycles here. So you also get a situation where there's not one solution to these sorts of more complex scenarios. There are actually a number of different solutions that you might actually end up coming up with. And so one of the challenges is to actually work out how to make this work in a distributed system, how to make it robust and reliable. And I'll talk a little bit more about some of how we address some of that within Corda and how we use some of the capabilities within Corda to actually solve that. One other thing to point out here is that's not a static graph. That would be changing in a real payment system. This would be changing constantly. So people will be making payments. People will be making obligations to make payments. The terms of those obligations will be changing all the time. So this graph is constantly changing. And that leads to another set of complications, and we'll talk a little bit about those later as well. So just to give an example of how things could actually be reasonably complex and some of the implications, I just wanted to give one example of one way of netting part of this graph out. So in this particular case, we're actually going to net out this one payment cycle. And so if you notice, all of these are actually paying each other in turn. And so there is a net solution that would be possible in which you make a smaller payment between each of them, and you can net out that entire cycle in one atomic transaction. Now, that's actually a very complex transaction. If you actually look at the number of payments that are being settled And if you actually put some real numbers in there, this is potentially a very large transaction involving potentially more than a dozen individual pieces. And we still want to make it as one transaction. So if you actually net that one out and you take that cycle out, what actually happens is this payment graph becomes disconnected. So we end up with two different parts of the network that no longer owe each other any money. And now I mention this because this comes up as an important problem, in that when we're trying to think about how to do this in a completely decentralized manner, distributed manner, there is no one party here who necessarily has visibility of everything that's going on. So the solutions we come up with have to be able to work and operate in a way where they can't rely on being able to reach everybody or talk to everybody, because that may not be possible. The information they've got available to them just may not let that happen. And in this particular case, I mean, the node C here is not connected to anybody at this point of time because it's made all its payments, everything's netted out for it. It doesn't have anything else to do. So I'm going to talk a bit about building this with Corda. And so I'll talk about the design concepts of what we did and what we've been thinking about. And this is still some work in progress. We're still doing some additional work here. And there will undoubtedly be more work here when we get to having the SGX capabilities available on the platform. And I'll talk a little bit about those in a minute. If we had zero-knowledge proofs, we could certainly use those in this as well. But this is actually building out the basic capability within a Corda environment. So our initial requirements were any node in this graph must be able to start this netting process. So when we saw that much larger graph, any one of those should be able to say, I would like to net some payments, or I'd like to call for netting to happen. The trigger for this could be time-based or needs-based. So one of those nodes could say, well, it's been half an hour since I last saw a net payment being made. I'd really like somebody to try and do something now. Or it could be that somebody mandates as a regulator that they would like it to happen every half hour. Or it could be that it's needs-based. Somebody in that payment graph may go, I really, really need to make a payment urgently. Can somebody help me by providing liquidity, by moving some funds around and making a net payment, and I can make some other urgent payment that I need to make. And the other thing is that participation is optional. So any node can decide what it's going to contribute to the netting solution, how it's going to do it, and why it's going to do it. If it doesn't want to, it doesn't have to. And so the whole design has to be robust against nodes deciding not to participate, and so that was one of our key requirements. So when we were trying to think about modeling this problem, I mentioned that all of those payments are actually obligations. They're not actual payments. They're statements that we'd like to make a payment at some point in the future. So we model these as obligations. These are essentially IOUs. If anybody's actually looked at the Corda code base and they've looked at the example code base, you'll see the IOU contract. And that's actually the basis of doing exactly what we're talking about here. All the payments are made against an obligation. So whenever we actually make a netting payment, we're actually settling against obligations. Each node in there gets to choose which obligations it's going to settle on what basis, and the priority for that. It's important because there may actually be multiple payment obligations going from the node, and it may only want to settle certain ones as a high priority. So it doesn't have to offer everything. And each node gets to choose how much cash it's going to inject, how much liquidity it's going to inject into the netting solution. So you don't have to provide all the cash you have. You may decide you only provide a very small amount. You may actually say, I'm not going to provide any cash. I'm only prepared to do this if it gives me a net inflow of cash, or it's net zero. Again, these are choices for the nodes themselves. So some challenges. We don't want to reveal everybody's information. So we have a bunch of unsettled payments. There's commercially sensitive information in there. We don't want to reveal that. I'm not going to talk about that because I haven't got enough time to talk about it. I'm more than happy to talk about it later. But we're actually using the confidential identity capability that has been mentioned earlier today, and it's available in Corda 1.0. I think this is actually one of the first real uses we've had for that. But that allows us to hide a great deal of detail about who's transacting with whom and on what basis. We need some fast convergence. We need this to happen really quickly. We really want to make netting happen in the order of a few seconds at worst. And one of the reasons for that is we can't stop the world. While this is happening, freezing a payment network is a really bad idea. I mean, if you needed to rely on techniques that were going to take tens of seconds to actually generate a solution, and you need nobody to make a payment during that period of time, then you've got a really bad payment system because nobody can actually do anything. And that includes people wanting to make gross payments. So this can't stop the world. It's got to keep running at all times. And I've mentioned before this need for atomicity, but no matter what happens, we must never be left in an inconsistent state. Transactions must happen fully or not at all. So there's nothing allowed to be incomplete. So how do we actually do that? Well, we have flows. We have lots of flows. And I think the estimate was that when we solved this particular problem on Corda, we were probably an order of magnitude more complex than anything that had ever been constructed on Corda before. So very, very high level, what we actually do is we break this problem into 2 stages. So the first stage is a detect phase, where we actually go out and we discover the network and we discover the opportunities to do something to net positions out. And then we have a planning and execute phase that actually go and make the transactions happen, if they're possible. So very, very briefly, I'll try and describe what we're doing. So this is a very simple example of the detect phase, and I'll do a very simple example of the execute phase. But if you imagine that much larger payment graph we were talking about, what actually happens here is we cascade this approach out. So we'll start with something very simple, and I'll talk about how it gets more complicated. So there are some interesting challenges here. Because any node in this network can actually start the whole approach, and any node can actually call for the netting, we have to allow any node to actually be able to make this work. So how does that happen? Well, any node starts the scan. In this particular case, we're going to say node A starts the scan. So what happens is node A talks to its neighbors. It talks to the people it knows, and that it knows it either has obligations from or obligations to. So in this case, B and C. And those red lines indicate that it starts the communication. So we use the Corda flow framework to actually start this conversation with those other nodes. So we talk to B and C, and we say to B and C, please tell us about payments that you'd like to contribute into our netting solution. And in the meantime, A also knows about the fact that it owes money to B, and in this case, A is prepared to make that payment or net that payment, so it records the fact that this edge AB exists. So it records the fact this payment exists. So nodes B and C continue, and they do the same thing. They propagate the message forwards. So they send it on to people they know about and say, we would like to discover more about this payment network and what's available that we might actually be able to net things out. And in fact, in this case, B and C talk to each other. When they talk to each other, what happens is both of them go, well, I've already seen this because I initiated a call to you. And so when B and C see that they've already talked to each other, then they stop trying to propagate any further. So they say, we've reached the limit of what we need to do here, and they start returning results back. Node C talks to D and says, please tell us about anything that you know about as well. So we carry on. D reports the information about the payment it owes to C. B reports the payment it owes to C. And so we now gathered some more information back again. And eventually, what we end up doing is we end up propagating all that information back to Node A. And Node A now gets a view of all of the payments that people are prepared to settle. Now, obviously, if we knew all the identities here, then that's revealed some sensitive information. I mentioned we have the ability to use confidential identities and confidential transactions. What we actually do is we use pseudonyms while we're doing this process. So there's a whole piece here that allows us to obfuscate what's actually happening and between whom. So once we've done this, what we've actually got is we've got a single node that's actually in a position where it can work out how to solve the problem that we're trying to solve. And it doesn't matter which one it is. If you actually started at B or you started at D, you'll end up with the same information. You'll just go a slightly different route. And so we use this flow framework to initiate additional flows until we actually get all the results all the way back, and we have a view of the payments that we'd like to actually try and settle. So we then get onto this planning and execute stage. So I'm not going to really talk about the planning stage very much. This is more of an economics problem and a math problem. But what we're looking for is we're looking for these payment cycles. We look to prioritize them, so we want to work out which ones we want to settle the quickest and which ones are the highest priority to settle. We compute what the solutions are, so the maths to actually do that's relatively straightforward. And then we have an interesting challenge. One of the things we have to then do is we have to get all of the participants in the netting solution to agree that this netting solution will actually meet their obligations. And that's actually slightly more tricky than it sounds. The reason it's a little bit more involved is that you don't know all of the people in this network. So all you can do is you can say, well, I know that I have these obligations I'm settling, and these are the ones that are being settled in this netting solution. And I know that I am either receiving cash of a certain amount or I'm making payments of cash of a certain amount. And I know that those balance. And so one of the things we actually have to do is we have to gather a series of signatures from all the various participants saying that they agree that they can settle out these transactions on the basis that all of the pieces that they understand all work. And when you get the full set of signatures over all of the facts, then we have a single transaction that describes everything, and everybody signed off on it and said, yes, this actually works. And the key thing is, if for any reason it doesn't work, then we're going to say, you know, this fails, the flow will fail, and nothing will happen. And then finally, once we've actually got these signatures, then we actually execute the net payments. And so we execute this one really large, complex transaction. So I'll talk a little about the execute phase. I just mentioned briefly what we do. In this particular case, we've got C is actually going to make a payment to settle to B, because that's the net that we're actually doing here, to settle this payment cycle we talked about before. And so what we do is we initiate another set of flows. This is the second phase I was talking about before. So A talks to C and says, you know, give me the details that will allow you to make this payment. I need to have a signature over it to say this payment's going to happen, on the basis that it will settle out this larger set of obligations. And C sends the appropriate replies. A then goes to B and says, does this satisfy you in terms of your obligations? So on the basis this payment's going to be made to you, does this meet your requirements? A's already checked for itself that it's going to meet its own requirements. It then does the same with C and says, you know, based on what you know you've got to pay and based on the obligations you're trying to settle, does this settle and meet your requirements? And once you've collected that entire set of signatures, then you actually have this transaction. And that's what we're actually looking for within Corda. And this is where we're using Corda's flow framework and its consensus mechanism to actually build that single complex transaction. And then when we finally do it, we finally send this transaction to the notary. And at that point, once the notary has actually notarized the transaction and we've had the finality flow so that all of the participants are aware that the transaction's been notarized, then all of them can update their states confident that everybody's done the same thing. And so this is a really big deal, because these three parties have actually now negotiated how they're going to do this one thing. So everywhere else we tend to often talk about two parties, but this is three parties doing it simultaneously. And in fact, there's no reason why it can't be larger. In that original graph I showed, we had a much larger number of parties who were able to contribute to a single netting solution, and we can build the same thing. So that's the essence of what we're doing in this netting solution. So it's a good example of some of the capabilities that we have within Corda. So why Corda? So Corda flows are incredibly powerful building blocks. And so we talk about Corda being used, and it was designed for regulated financial environments. But actually, this problem is not really a finance problem. This problem is actually a networking problem. And so what we're interested in doing is we're interested in building out something that can do a complex network protocol exchange, and using this framework to simplify that, and then to get a single result at the end of it. So we end up with this distributed atomic transaction. And so what I find really exciting with Corda is that we can actually build these really complex atomic operations, because they're something that are very, very difficult to do in the vast majority of platforms, if they're possible at all. And yet we can also use this to solve all sorts of interesting problems. Anywhere where you need two things to move at the same time is an example of where you'd need an atomic transaction. I've been talking about cash, but if you actually wanted to exchange cash for some other asset, you have the same problem. You need to be able to exchange two assets simultaneously between two or more parties and have that happen either all or nothing. And so this is something that Corda allows us to actually do. So we can build these very, very complex transactions. And the nice thing about this was that this actually was a relatively small amount of code. So our dev relations team, so you saw Roger, there's also Richard and Case. They actually built this in a couple of weeks. And I think we're well under 1,000 lines of code in total for the entire system to do this complex netting, including the whole confidential identities piece. So this is actually very compact. And one of the nice things that I'm seeing with Corda right now is that each version we're doing is getting smaller. It's actually easier to represent these concepts each time we build a new version of Corda and we provide a new release. So you know, my challenge here is to say, you know, look for these sorts of problems. These are the really difficult problems to go and solve, because we think we've got a fantastic tool that will allow those things to be put together and allow them to be put together in a way that's very easy for people to use. There's no really complex protocol engineering here. The flow framework does all of that for you. So Finally, I mentioned this is more than just a theory, so I get the one bit where I get the video, and hopefully this works. There we go. So here is actually, we have our debug framework running, and some slight artistic license, but actually we will get to the real bit, which is actually showing the Corda bit doing it. And so actually these are the models of some of the obligations that we're actually dealing with. We can visually represent them, and we actually see some of the payments, and we'll get to the network simulation in a second. And we can actually see all the various pieces pinging around as they actually compute and actually distribute that atomic transaction. So we actually have this running right now on M14. So thank you very much. Are there any questions?
Might be a very stupid question, but I guess having done this with my friends when at uni, a lot of times the standard way of settling these kind of things is you just pay everything into a pot, and you pay everything out of the pot, i.e. I owe 5,
Yep.
you get 3, you get 2. It's much less complicated than doing all this graph, and it actually gets the anonymity. So why doing this complex dance when you could just say, you net out everything on every single node, introduce an additional node that nets out to 0, and that is the center of the transaction?
Okay, so the question was, why don't we use a single node to coordinate the whole activity? There's 2 reasons why we didn't actually want to use a single node. First of all, it introduces a new single point of failure. So that was something we wanted to avoid, so that netting node would actually have a pivotal place within the overall payment system. The second thing was that that netting engine then ends up being a trusted entity. It's going to actually take a bunch of cash in as a single transaction, and it's then going to make a payment out as a single transaction. It's a law unto itself at that point. There's no way to constrain what it's actually going to do. So there was something we were very keen to avoid having to do. There's also another part to this, which is that within a single environment, we can actually we potentially have a single entity that will actually deal with that netting. And then, in fact, if you're dealing with something like a real-time gross settlement system, that entity is the RTGS. But if you actually wanted to have more than one type of asset, and Corda is designed to allow us to have many, many types of assets simultaneously, then you might actually want to say, I have a netting arrangement that I have with this set of peers on one side. I have a netting arrangement I have with a different set of peers for a different set of cache states or a different type of asset class. And we want to be able to have as many of these as makes sense from a business perspective. Introducing those sort of Oracle-like functions or those special purpose nodes makes it more complex to do that sort of thing, and it makes it much more difficult to actually think about how you would build these more decentralized payment schemes.
So I forgot who was second up here, sorry. Yep.
Hi, Dave. Thanks for the presentation. Fascinating. Robert Olson, Radix.global. I'm really interested, Mike might remember the Christmas party, about scalability. So what's your flows per second or operations per second?
In terms of the netting?
Yeah.
So right now, we're actually running in simulation for most of this. The gather stage is running in a few hundred milliseconds. I think the whole thing's running in the order of a couple of seconds. I mean, that simulation we actually ran was actually slower than we can actually do that right now. In terms of the scale, the algorithm's designed to scale really fast. So the detect phase is, worst case is 2n, based on n being the number of nodes that are actually participating. Typically, it's going to be much better than that because you're going to have some tree structure there, so you end up with some logs in there instead. But the worst case is 2n. And what our expectation is that typically you'll be doing this in a relatively close geographic proximity, so you'll actually find that the latency isn't going to hurt too badly. In terms of the transaction building does involve a certain amount of work because you have to send out quite a lot of messages, and it's basically scaled in terms of the number of messages that you need to send to the various nodes that have to sign signatures. So there's a reasonably involved part to that. But one of the reasons that we actually have this thing set up and we want to make everything atomic is that other payments can carry on while this is happening. So this doesn't preclude anybody from making gross payments or even making other netting payments while this is happening. This whole flow that's actually constructing the netting payment, it can run asynchronously from another flow that's doing something somewhere else. So in terms of scaling, we're not actually constrained. We don't have to serialize, for example. The other thing is if we're actually doing this across asset classes, we have the same thing again. There's no constraint that actually serializes anything between asset classes.
Well, I just had one quick question. Like, what do you do for an error case? Like, say if you have like 3 different ones of these going on, and all of a sudden one of the nodes is out of cache,
Okay.
or whatever. Like, how do you roll it back?
Okay, so you don't have to. This is one of the beauties of it. So within the flow framework, if you actually ask for the signatures over the various cache states that are going to be represented in the overall solution, if somebody is unable to actually provide that cache state, they can't actually put that signature over it, the flow fails. And when that fails, you actually collapse out this attempt to provide that execution. So you can still use the detect phase of information, and you can simply fall back to the next payment that's the next best case. So you can say that node's badly behaved, it's unable to meet its obligations for whatever reason. We'll find a netting solution based around the ones who are left. And the same goes for if somebody makes a gross payment at the same time. If somebody makes a payment out, or somebody actually unilaterally settles an obligation that they'd previously declared they wanted to solve, that will actually fail when we go to collect the signatures, and we'll simply fall back to the next one that's available.
I think we have one more question. I'm going to go to somebody new, sorry.
Thanks. Why is it better than the current way of doing it? There are central banks all around the world doing real-time gross settlement with batch netting for smaller payments. So why is this going to be better?
So there are a number of different scenarios where it's not that this is actually better, it actually allows a few scenarios that don't exist within that RTGS environment. So the algorithms that we can implement are equivalent. So within a single regulated environment, you can get equivalents with the RTGS system that you'd have right now. But where you actually gain is you gain from the ability that if the RTGS system is offline for any reason, people are still able to perform some form of liquidity saving. So there's a resilience aspect here. And there's also this aspect that you can actually construct additional liquidity saving groups. So if you actually want to have participants in different parts of the world who want to have a liquidity saving or a netting solution for the asset that they're dealing with across different geographies and potentially different regulatory domains, then you can actually build those with this sort of environment. Whereas if you actually had to do the same thing in a more more traditional sense, you'd have to have somebody who's going to be the entity that would own and operate and manage that netting engine.
Great. So I think because of the time, so apologies for the questions I didn't get to, Dave will be here.
I'll be around, yeah.
So we'll keep Dave with us. So thanks, Dave. Great presentation. So before we head off, my one call to action for you guys, head up to LinkedIn. That's just a short URL to help you there. We'll keep driving this content. So we've been video recording all of this. We'll put this up. We'll put a link up in the LinkedIn channel. Is how we're going to let you know when it's available. So the slides, the video, will all go back online shortly. So we just got to do a little bit of editing to get it together. So, and before I have everybody leave, if you were a speaker, please stand up. And if everybody could just thank the speakers. There's a few in the back. Thanks, guys. So I know a lot of time went into preparation for this, so thanks a lot. So drinks. So downstairs, we have the bar to ourselves. So if you haven't overextended yourselves into your evening obligations, please join us downstairs for a drink. The speakers and everybody should be around for a while. So thank you, everybody.